We're going to talk about solids. If you'll let me finish writing the title on the board. This unit is really a hodgepodge of topics. So I will adjust the title as we go. Today, we're going to talk about solids, liquids, and gas. You can put miscellaneous if you like. Now, we're going to start by talking about solids, liquids, and gas. We're going to go to equilibrium in this unit. We will finish equilibrium. We will do kinetics, and we will also do thermodynamics. So there are lots of things that we will do in this unit. This is a large part of the curriculum, depending on how the state test is structured at the end of the curriculum or the end of your course. You could see multiple questions on this particular unit on the exam. Because I never get to see the exam, I don't know. I can tell you from release items that a lot of release items come from this section of the curriculum. Okay? Now, a lot of people ask me, why don't you teach this at the beginning? Stuff would make no sense if I taught it at the beginning. You don't know anything until we get to this point. Okay? So things should start to click more as we go through these topics. So, yes. But you just know more now. Now, we're going to talk a little bit about some things you should already know. I don't think I have any pre-typed. Yeah, I don't think I have pre-typed notes for this. Let me look real quick, but I don't think I do. It was in your notes. We're going to talk about kinetic molecular theory. Really? That's a shock. I would have never guessed that.
That's why we're doing the electronic theory or some theory.
No, electronic.
Definition.
Yeah, I don't have Alright, yeah, I don't have anything typed. You're going to have to deal with my terrible handwriting. Alright, so if we talk about solids, liquids, and gases, going back to KMT for just a second, there are several folks who got this wrong on the test, even though I told you it would be a test question. Alright, KMT applies to what?
Solids, liquids, and gases.
Exactly. Okay? Yeah. It would apply to plasma also. I don't list plasma up here when I teach this topic because it's not part of our curriculum. But it would also apply to plasma. Okay? The sun. It's another state of matter. But the sun is a good example. Now, when we talk about kinetic molecular theory, okay, all states of matter have movement, okay? Several people did exactly what I told you they were going to do on the test. What state did they tell me did not have matter? Solid. Some people actually picked which state of matter is the only state that had motion. Okay, and I realized we were studying the gas law. So it's real easy to be distracted by that when you're answering a test question. However, all states of matter have motion. Now, just to refresh, motion stops at what? Okay. 0 Kelvin is defined as absolute zero. Now, absolute zero is 0 Kelvin. Okay, now, it's all well and good to know that's approximately negative 457 degrees Fahrenheit, but you need to know it's 0 Kelvin. Everybody okay with that? Where's what I want? All right. Now, I've drawn this for a couple people, but not very many. If you consider, and you should have seen this before in some other science class, this should not be new. If we consider the three states of matter, solid, liquid, gas, right? Let's just say that this is a solid. Now, can you tell in my crappy drawing that my particles in a solid are fixed and close together?
Yes.
Can you tell that my particles in a liquid are much, much closer together but able to move around? And that there's a lot of space between my particles in a gas? Can you tell that?
Yes.
Okay, then I didn't do too bad on my drawing. Now, we want to look at, and we're going to draw a table with this in just a second. We want to look at how a solid, a liquid, and a gas are different based on their arrangement, based on their attractive forces, and based on their motion. Okay? And we're going to reference these three pictures to do that. And I'm going to give you a chart and let you explore some properties amongst these three. Hopefully it will be reviewed. Hopefully. It should be. Nope. Well, in any other science class, doesn't necessarily have to be across the street. It could just be things that you should naturally know. I don't like rocks for soil either, so it's all good. All right, is everybody have what they need? Yes. Okay. So, I want you to draw a chart. Okay? We're going to put, let's put arrangement first. Let's do motion second. And we'll do attractive forces last. No. And we'll do gases first since we've already studied those. We'll do liquid second, and we'll do solids last. Man, I'm going to try to draw some lines that are reasonably straight.
Well, if the lines are.
Yes, what I do.
Yes, Daniela, I know they're supposed to be, but, you know, I don't know what you want to call mine. I was attempting to draw non-straight lines, so I don't know what we call them since, you know, lines and straight are the same.
I'm not good at this.
So I need to know what the correct term is. Yeah, go ahead and get back to them. We're running a lot. All right, everybody caught up?
I'll go right back.
So for gas, what can you tell me about their arrangement? Okay. Do they have an arrangement?
No.
They don't. Okay. They have absolutely no arrangement. All right. Now, based on the loose, and Queen said what? What'd you say? You said loose. What'd you say, Queen? Their movement. Hold on to motion for movement. All right. So if we're going to say loose, what could you say about them? Are they far apart or very close together? They would loose. All right, so we can say the gases are very far apart. All right, so their motion, what were you going to tell me about their motion? Are they fast or slow? Fast, okay? Now, they are the fastest moving particles. Why would these be the fastest moving particles? They have more. You are. I think you're just using the wrong word. I thought I heard somebody say it. They have more space to move around. Okay? They're the fastest moving particles because there's more space to move around. Sort of like in elementary school. When you had more space to run around, you tended to move more and run around more. When you were in a classroom or an environment that didn't allow you to move very much, you were more contained, you sat in a chair more often, you were more still. But put you guys in a gym or a larger area, and what did you automatically do? You jumped out of your chair and you ran around like a crazy person. All right? Gas molecules are the same. Give them more space, and they move around from more. For example, one of the properties of gases we studied is their ability to expand. If you put a gas in a bigger container, do they all sink and settle to the bottom? No, they expand and fill their container from top to bottom. So they're the same way. Put them in a big open space, do they sit in the corner? Now, you might find one who will, but the vast majority of them do what? They run around like crazy. Okay? Now, attractive forces. What am I talking about when I say attractive forces? No. What? No. I love asking this question because y'all never remember. You're on the right track. Yes, polar and non-polar, so where am I going with that? Yes, one of them does.
Dipole, London.
There we go. All right. So we're talking LDF, dip, or dipole. And the hydrogen bonding. This is why some of you are still struggling with these concepts. LDF was what kind of attraction? London, we can start there. London was an attraction between what? Non-polar molecules. Okay, dip was an attraction between polar molecules. Hydrogen bonding was an attraction between a hydrogen and a lone pair. Okay, so basically we're talking about who does attract more or less here. So if I'm a gas molecule and I'm running around like a crazy person, can I attract somebody else who's running around like a crazy person? I'm running around too fast. I can't get close enough to attract them. Okay? So these are very weak. Okay? These attractions are very weak because the molecules, again, I go back, I think it was Kathleen who said it, because they're so far apart, they can't attract very well. Okay? Wrong way. Too far apart to attract well. Okay? They're too far apart to attract well. Now, if we talk about a liquid, we want to compare and contrast that. So how does the liquid compare? Okay? Does it have an arrangement though? Is it in some type of fixed pattern that we can identify? No. Okay? A liquid still has no arrangement, but what could you tell me about its distance between its molecules when compared to a gas? All right, they're much closer together. All right. All right, they're much closer together. All right, what could you tell me about their motion? All right, hold that when we talk about properties. What happens when you compress air? The molecules get close together. It would liquefy eventually. We change states. No, we can't. I don't have the equipment to do it now. What happens with motion? Okay. Why would it be much slower? Okay. There's much less space to move. For example, if I send you up the main hall right now and said, go to the office, it's an emergency, could you get up the main hall right now? If I said it's an emergency, somebody had just beat the fool out of David. I got mad. I jabbed him with my pen. He's bleeding profusely on the floor. It's an emergency. We have no first aid skills. Get to the office in a hurry. Could you get up the main hall in a hurry? Assuming we could get out the door. Could you get up the hallway on the main hall? Yes. Why could you get up the hallway on the main hall? There's no one there. It's like the gas molecules. There's plenty of space. You can race up the hall. Now, when the bell rings, can you race up the hallway? No. It's like the liquid molecule. What's in the way? All those people are in the way. You've got to shove and fight your way up the hallway. That's the liquid state. You can still move up the hallway, but it's a constant battle of trying to weave your way around and push people out of the way. Okay? No, I would never interview David. Okay? Now, the attractive forces. How would the attractive forces in a liquid compare to a gas? They're much stronger. Okay? All right, much stronger than gas. Why would these be much stronger than a gas? They're closer. Okay? They're closer together. The particles are closer together. It's all about proximity because the particles in a liquid are just closer together. It's easier to attract. Okay? Because in a gas, they're zooming past each other. It's hard to attract. But if I'm a gas molecule and I'm zooming past, I don't have a hope of attracting. But if I'm a liquid molecule and I'm just sort of roaming around and circling around there, you're close by over here, do I have some hope of possibly sticking to it? Yeah, I'm in the vicinity of it. Okay? I can't get very far. All these people are circling by me. I can't escape out of the vicinity. They're bumping up against me. I'm bumping up against them. I'm likely to stick around. Okay? Alright, I can't escape. I'm likely to stick up against it. Now, how is that going to compare to a solid? They do. Okay? A solid has a fixed geometric pattern. Change colors again. Alright, solids have a fixed geometric pattern. Alright, to relate this to what we've already done, in an ionic compound, we call it a crystal lattice. Okay? So if you break the crystal lattice, the structure does what? It shatters. It's brittle. It could possibly break into a unit cell, but odds are good it would not because there are millions of those that would probably not break into one individual unit cell. It could, but probably not likely. It would break into a smaller crystal. It would probably shatter. A lot of the stuff that we use here is Pyrex, and we can use Pyrex with a lot of varying temperatures. But even then, I would not recommend you get it really, really hot in a Bunsen burner flame and then put it in really cold water. because even that could possibly crack or shatter. It won't shatter like your glass will at home, but it could crack it. Let's not. All right, we're poor. I'm not going to get replacement glassware from Miss Curry because we decided to see how it would crack. All right, so the motion of a solid. What is the only thing a solid can do? Very good. It can vibrate only. Okay, and you should remember, even though we didn't say this up here, these two can do what? We've already learned these. There you go. And I'll write these up here for either of anybody who might have forgotten. Rotate and translate. Okay, so gases and liquids can rotate and translate, but solids can vibrate only. All right, and I'll put in place. So remember, they're in fixed places. So if you're in a fixed geometric pattern, when you vibrate, you can only vibrate in place. You can't move anywhere. You're stuck in that position. And what can you tell me about the attractive force of a solid? They're the strongest. Exactly right. They're the strongest because they're the closest together. Right? They're the closest together. Any questions? Truthfully, I have no idea. I've never studied philosophy, so I couldn't say. It's been way too long since I've been in college to study that. One of those, if you don't use, you lose. You lose, TJ. 91.
Yeah, you will all 27. Yeah, so you guys are not even close to it. I started teaching in 1991. I was 21 years old when I started teaching. I did not graduate. I was an old state. I was a small town called Wilson State. I have always taught here. Wow. I've always taught in this room. I always in this room. I have to count. I have always taught in this room. What? I have taught now. In this room. In this room. What? I have met her yet. Yeah. What? If you like met so many graduating it would be very hard to say. Very good. Now, you will. The paper I just told you, I would like for you in your study, no more than 3. I did not set out in the study because every year I do, they're like falling on you. So I didn't do it. I need you to take those properties if you see below the bold word, and I need you to figure out if those properties fit that with the full thought. Some of those properties are going to fit in more than one category. If there's a word you don't recognize, I need you to define that word and put it on that sheet of paper. You will be keeping this as part of your notes, okay? But if I don't know what I want it out, you're welcome to one of those. You don't have to do it. I don't think. We are going to go over this. N is 9 p.m. I will say 9. Okay? Then you go. No more than 3. If you don't know a word, you are allowed to use your phone, and I will tell Mr. Curry that I gave you permission to look up the answer on your phone. No more than 3 people per group. There's no more than 3. A group of people. No one was started. It's not the story. No, it's not. I didn't know
So what? Doesn't mean you're going home. I mean, it would be most fabulous if you all got to go home. What if I would not count on that? What if everyone just walked out the door? They can't do that. People can jump. For people who are at short end of the time. But you still wait. Yeah, that's fine.
Filipino, Malaysian, and Irish. I didn't say nothing about Malaysian. Filipino, Malaysian, and Irish. Who says?
But let's just say that there are no people. Everybody knows the water. It's law.
What? Oh, yeah, look at that.
It's not still water. It's not so even if it's like really I bet like I know you put the most right in this one because I also wait, so you're one of those I think an hour and a
All right, got it done? All right, move back to your seat.
I was gonna say something like, oh, but
Oh, what we got wrong? It's just not with water. What you get at the grocery store. Oh. Yeah, but you buy probably 90, 10, 50, 50, 70, 30, that's 100%.
So when it's like 99.9%, something like that, so
Yeah.
like for diabetes purposes,
Yes.
but this is really complicated, it's not.
I have no idea. That's just 100% rubbing alcohol.
Is this the good stuff?
Rubbing alcohol. Is this the good? No, I think anything you want to drink. But you go ahead. The heartburn will probably be wicked. All right. So, if we look at what you came up with, why don't I try it?
Yeah, it is. No, I'm gonna be,
Oh, this is where I was doing.
Instead of y'all asking me.
I'll go to that document. I will get that. Yeah, all I did is,
I bring my phone.
Okay. Never mind.
I did that this morning.
So they fixed the computer issue. Can't do that either. I guess we're gonna go old school and use the overhead projector. I didn't get out.
Oh, man. What?
Oh, it's all working.
She was gonna explain it to you. So we're having an issue with the two computers and trying to figure out limitations of that one and this one. We can't get the smart notebook right on this one. It's a huge issue right now. All right, so what do we have on the far left side of your sheet? So I keep it in the same order.
Fluidity. Or left.
Solid, liquid, and gas.
Yeah, that's what I gas.
Oh, you said this.
No, I think gas.
Okay, in the middle
Liquid.
and on the far right. Which is why I was trying to show it under the data projector so that it looks the same. But all right, So, give me something that you put under gas. Fluidity. Alright, so, we talked about fluidity when we studied gases. So everybody should know it has the ability to flow. The fluidity definitely goes here under a gas. Did we put it any place else?
Liquid and
They can't move. They're in fixed positions. So if you put fluidity under a solid, you need to do what? Erase. Take fluidity out from the solid. Remember, the solid has fixed positions, right? So can they move? No. So they're not fluid. All right. All right. What about the next one? Let me just do these in order or I'll skip them. Low density. Where'd you put it?
yeah.
All right. So low density is here. All right. Since we're doing density, forget the order. Where did you put medium density and high density? Since I probably have all of those on there.
I just use all.
Okay. Middle density here and high density here. Okay. And do we know why? Okay. The solids are more dense because they have the highest mass and they have the lowest volume. So when you divide, you're going to get the largest density. So they're going to sink if they have the highest density. They float if they have the lowest density. Okay? So evaporation, where's that going to go? Who's going to evaporate? Liquid? Okay. Liquids evaporate. And we're going to talk about state changes most likely on Monday. We might get to start it today, but we won't get far. Compressible. Who could be compressed? Gases are compressible. All right, let's address that solid that Tyshawn yelled out. All right, if we go to solid, look at my picture of a solid. Can these particles be pushed together further and compressed? No. Okay? You cannot compress a solid. So that's a no on the solid.
For some reason, I'm thinking of
No, it cannot be compressed. Who can freeze? Who freezes? Liquid freeze. Can a solid technically freeze? No, a solid's already frozen. Liquids freeze. Alright, who has definite shape? Solids have definite shape. Alright, definite volume. Alright, I heard definite volume on solid, and I heard definite volume on liquid. Both of those are correct. Alright, solids have a definite volume, and they have definite volume on liquid. Get off the phone, Jordan. Jordan, get off the phone. No, but this one is. I was just looking at you to see if you were guilty, but I knew that one was.
I was reading my picture.
Okay. Oh, thought I was getting to the price one.
I was
For liquid?
Yes.
No, like my drink here, this has a large size cup, let's just say it's 25, 26 ounce cup. Every day it's going to be a 26 ounce cup. The volume is not going to change unless they don't fill it half full, but it's still capable of having 26 ounces put in it. Yeah, most likely. Alright, relatively incompressible. Who is relatively incompressible out of those three? Liquid. Liquids have a tiny bit of space between them. However, given that they have this tiny bit of space, they are pretty much incompressible. So Daniela and all of them were hypothesizing at the back of the room, if we have water in a cube, can we compress it? For the most part, no. Okay? You cannot compress water. There's a little bit of space. You can compress it a little bit, but not very much. Okay, liquids are generally incompressible. Surface tension. What has surface tension? Liquids. And that's what I'm trying to demonstrate, which is why I was trying to get my data projector to come on, which is why I said I guess I'll go get the overhead projector back out of the room. Yes. Okay. But I also want to demonstrate it for miscible and immiscible for after Christmas. Expansion we've already talked about, so where should that go? Gases have the ability to expand, which would be fabulous if my Pepsi would just expand to fill my bottle every time I drank something out. It doesn't have that ability though. I know, that would be so cool, wouldn't it? Yes. Diffusion, especially the prices of those things. Oh. Diffusion. What diffuses? All of them. There you go. All right, so if they all diffuse, can we put some more or less on here somewhere? Which one is going to be the fastest? This will be the fastest diffusion. And again, it would be the fastest diffusion because the particles are the furthest apart. This would be the slowest diffusion. And by slowest, I mean like perhaps 20 years to get some solids to diffuse together. It's going to be incredibly slow. Like if you see clamp two metals together, it might take 20 years, maybe 30. It'll be a while. They will eventually diffuse. Oh my God, I could be dead, people. You can do it at your high school reunion. Put it in the box. Let me not turn that into full on. All right. Not compressible. Not compressible. All right. Yeah, I'm in the right column. Not compressible. And the last one is middle density, very done. We've got them all. All right. I wanted to demonstrate surface tension, mainly because it goes to the topic that we're going to do after Christmas also. And it's one that's an easy one to demonstrate. But normally I do it with the stupid document camera, but we're having technology issues, so I'm going to have to go old school and get out the overhead projector. I can't hear you. Oh, where's definite melting point going to go? Sorry, I didn't. Thank you, Victoria. I didn't realize I missed that one. Definite melting point. Nope, I missed it. Sorry, thank you.
Yeah.
All right. So, first of all, what is surface tension?
Something else.
Huh? Oops. That's supposed to be an N, not an M. The ability of adjacent molecules to attract each other. Okay? The ability of adjacent molecules to attract each other. They don't bond. Okay? There's no bond that forms between them. They essentially just attract each other and hold each other together. Yes. Okay? So, if I was in physical science class together, I would refer to this as a force. Okay? Okay? We're all about forces in physical science. So we call it a force. The push or a pull. Now, what kind of molecules would you all give a rest back there? I was done pretty well today until right now. All right, what types of molecules have good surface tension? And then 4 surface tension. That's the reason for my demo. The reason I'm dragging out that stupid overhead projector. Which one is good, polar or non-polar? Which one's good, which one's bad? That's right. Guys, polar molecules are good, and non-polar. It would require something extra to break it. So water, for example, would have what? It's polar, so it would have good surface tension or poor surface tension. It would have good surface tension. So you guys all know that water is a polar molecule, so it has good surface tension. The example that I have for poor surface tension is alcohol, or plain old rubbing alcohol. Let me put that up here before Ty Schoen's asking me about drinking it again. All right, I've got rubbing alcohol or isopropyl alcohol out because it's a non-polar liquid to illustrate that it has poor surface tension. Okay, and hopefully it'll work. It doesn't work particularly well with using the smart board. It works really well with an overhead projector. So, but getting it to show on this board is a pain. All right, let me grab this antiquated. It's prehistoric.
No, I remember you go back in fourth grade. You like had big hard days.
Yeah, but then, text stuff.
Yeah.
You went back of the room, right number 4. I was like, oh. That's bad.
But I didn't ever get an overhead projector. I had a chalkboard.
Remember that was I never did that board.
I did a little bit. They have like iPads and the coolest thing is like
Wait, the only person I know that took accident actually.
Just the front one. The front one. Let me see what I've got with the front one on.
oh, I think I know.
Yeah, that'll probably work.
I can see a rainbow.
Yeah, I'm sure you
I think we're going.
All right, let's see if I can get it to work. Man, yeah, I need it to be white up there.
Oh, wait, I'll make a little bit.
David don't care.
Oh, wait, that'll be nice.
No, I don't want to. I can save it myself.
Hey, for the view.
I'll save it.
That's a good plan.
Oh.
I like trying to.
I'm the next, right?
Yeah, just like right there.
This is so sad. Modern technology, and I've got to go old school and put paper all over the smartboard.
We don't have no problem.
That's like legendary. was going, the
Get
high
it
school
for
band,
it.
Hall of Fame.
Alright, now let's see if I can get it lined up with the paper. Struggle is real, people. A little fuzzy. Alright, now let's see if I can do anything to adjust this now. Anything? Hey, don't y'all laugh. This is working. Alright. Now, not the most attractive thing on the planet, but it's working. Now, you see all that dark line all around there? Alright. It moves. So, that is water, and it looks like it's got a little alcohol mixed in based on that edge. Now, if I switch to alcohol, but I got water in the thing. Alright. Alright, that is not on the paper. Try that. Now, see how it's dark on the edge? That's the water mixed in. But see how it's spreading all out? And it's going all out and it's just spreading out? This one has good surface tension. That's the water. It's got that nice dark outline where it's trying to stay beaded up. This is spreading out. It's just running away. That has poor surface tension. This is a polar liquid. That's a non-polar liquid. Now, the reason I spent time doing all this stupid stuff is so that I could put the two together, because after Christmas, we're going to talk about what happens when you mix polar and non-polar, and it's a topic called miscible and immiscible. So let's say that I take this polar liquid and I put it in this non-polar liquid. Does a polar liquid mix with a non-polar liquid? Yeah, the polar liquid doesn't like the non-polar liquid. So the polar liquid, yeah. So the polar liquid is trying to do what?
Why is it that?
So if I put some more non-polar, so if I put the non-polar liquid over here, what's the non-polar liquid doing? It's pushing the liquid away. So if I take some water and I put, no, it's just trying to get away from it. So if I put some water right there in the middle of it, what happens? It's trying to get away from it, and it's going to try to get out of it, but it's drawing itself together in the middle of that non-polar liquid. It's going to form an island. It just doesn't mix. It doesn't want anything to do with that alcohol. It's going to try to get away from it.
What happens if you put the alcohol in the water?
Again, the water just tries really hard to get out of the alcohol, and it'll break itself up into little pieces to try to get away from it. But it's not. It will eventually, and it'll work hard to break itself up, and it'll work to get away from it because it doesn't want any part of that.
Is there a reason why whenever you pour the alcohol, it's like
For surface tension, it's a non-polar liquid. It just spreads out. There's nothing to help pull it together. No force to pull those molecules back in to hold it together. Okay? Everybody got it?
Yeah.
All right, let's talk the two types of solids so that on Monday I can just talk state changes in math.
Right.
All right, let me yank down my heavy-duty technology here. There we go. High-tech stuff right there.
So we're going to use that thing for the rest of the day?
No. I didn't rate one of those back in the day.
Yeah, what?
I had chalkboards that went from that wall all the way to that door frame, and I had, oh, wow.
I just don't need to.
My first smartboard, it was a little odd getting used to it, to be honest with you.
So I had chalk. I wrote in chalk for the first 16 years I taught. I erased every period. Wrote again.
They
Wrote
really
again.
like it gets to the right.
Huh? I have been known to hurl one and hit him in the head. Got pretty good with mine too. All right, two types of solids. All right, two types of solids. Number one is crystalline. Yep. Everything that's a crystalline solid has a crystal lattice. And number two is amorphous. And you cannot tell me if we have a quiz that A word. It will not be an acceptable answer. All right, crystalline and amorphous. Now, a crystalline solid. What do you suppose a crystalline solid is? It has a definite geometric pattern. Exactly. And it melts at a specific temperature. Okay, so there's two things, two requirements to be a crystalline solid. You have to have a definite geometric pattern, and you have to melt at a specific temperature. That's called a definite melting point from the list that we just talked about. Huh? You're talking about 212. Oh, for water, yes, if it was an ice cube, it would be 212 on the Fahrenheit scale. But remember, we're not only going to talk about water. Okay. Now, for amorphous, you have a random arrangement of particles. And you melt over a range of temperature. So, random arrangement as opposed to fixed, and you melt over a range of temperatures as opposed to specific. Now, example. What kind of things might fit in here? Well, for crystalline, salt, sugar, ice are three that you're all familiar with. Any of you who like diamonds? There you go. Until you get one.
I like.
Find one you like. Emerald. Any kind of jewelry that you might like. Topaz, emerald, rubies. All of those are going to be crystalline. Okay? Now, amorphous, just to give you some differences. Things that are random. All right? Wax, tar, plastic, rubber, putty, anything like that. Modern day slime, if you know anybody who's into do-it-yourself slime. You don't want to know how much my house has been overrun by slime.
Oh, yeah, yeah.
It's like man-made.
And we still have slime.
Oh, yeah. I don't know how people like slime. I find the noise.
I find it satisfying.
I find the smell.
Nothing satisfying about slime. All right? Wax, tar, plastic, rubber, putty, fiber optics. We would not have the computer technology we have today without amorphous solids. If you have Christmas trees with those fancy lights that change, not the regular light bulbs, but the fiber optic lights, those would fit under amorphous. Okay? Now, I'm at 9:47, so I probably need to stop. Your homework for the weekend is what? Your lab report. Now, on Monday, we will talk state changes. Now, I'm not just talking solid, liquid, gas. You've got to be able to read a graph. You've got to be able to calculate the state changes. Your first quiz on this topic will be on Tuesday. Okay? Just so you're aware. Remember what